All right, 9.1. Today we're going to start our chapter on probability. And 9.1 is just going to be determining probabilities in simple situations. Simple meaning like there's a one case thing. So for example, in this section compared to next section, we're going to be rolling a set of dice one time, right? Or something like that. Whereas in the next section, we might be rolling the die twice. Okay, you're doing it twice in a row. And that complicates things. So to start with, an experiment. An experiment is simply an activity whose results can be observed and recorded. A lot of what we do in Chapter 9 is going to feel like games. Okay, different types of games that people play. But they are experiments for the purposes of what we're looking at. An outcome is each possible result of an experiment. So if you roll a single die, right, numbers 1 through 6, the experiment is rolling the die. The outcomes are each of the individual sides of the die, could be what shows up when you're rolling it. The sample space is a set of all possible outcomes for an experiment. So that would be like a listing of all the things that could happen. So my die example, I would list the numbers 1 through 6, and I put them in curly braces. That's how we list them. And then an event is any subset of the sample space. For example, it could be rolling an even number on the die or rolling a prime number on the die, right? So some sort of a smaller category. All right, Theorem 9.1 talks about the law of large numbers. It's credited to Bernoulli, sometimes called Bernoulli's theorem. And it says the following: if an experiment is repeated a large number of times, the probability approaches a fixed number. Think about flipping a coin, for example. If you flip the coin enough times, you would expect over the course of time to have an equal number of heads showing up as tails. It has to be a very large number of times for that to make sense. You can't do it just 5 times, right? And the same is true for things that are skills-based, right? So I have 2 children in my household who like to play basketball. If you ever watch like NBA basketball, they like to keep track of statistics on the screen and tell you their percentage at the free throw line, for example. Well, it doesn't change that much over time, right? Like they have to get significantly better or significantly worse for that percentage to adjust very much. Okay, as an average, that fixed number is what this is talking about. Probability is calculated as the number of ways a certain event can occur over the number of items in the sample space. So let me give you an example. Let's do our sample space was my dice. 1, 2, 3, 4, 5, and 6. So there are 6 items if I'm doing that down here in the sample space. And if I want my event A or my outcome A to be evens from up here, right? There'd be 3 of those. So it's just counting. There's 3 even numbers out of 6 total numbers. There's a 3 out of 6 probability that I would roll an even. And we would reduce it just like we do with all of our other fraction stuff. Sorry, I'm kind of all over the screen. We would have a probability of 1/2. The number of ways our outcome, whatever the outcome is, compared to the number of outcomes that are possible. Mutually exclusive events are events which have no elements in common. So what would be a mutually exclusive event to rolling an even? How about odds? Rolling an odd would be a mutually exclusive event, right? Even, odd, nothing in common, yeah? So 2 events that have nothing in common. Now, my even and odd example take up the whole sample space. They wouldn't have to be mutually exclusive. For example, I could have event A is rolling a 5 and event B is rolling a 6. These are also mutually exclusive. They cannot both happen at the same time. I cannot roll both a 5 and a 6. All right, with any probability, there's always between 0 and 1 likelihood that it can happen. The 0 and the 1 are very much like what we would think of when we think of percentages. 0 is 0%, 1 is 100%. Everything happens with a 0 to a 100% likelihood of happening. I can't have a 110% chance of rain tomorrow, right? It's always between 0 and 100%. So the probabilities that correspond to that are 0 to 1. Theorem 9.3 says that the probability of an event is equal to the sum of the probabilities of the disjoint outcomes. For example, if I wanted the probability of rolling a 5 or 6, I could find the probability of rolling a 5, and I could find the probability of rolling a 6, and I could sum them together and add them. Right, so instead of looking at the sample space and saying, oh, look, there's two numbers that are 5s and 6s, so it's 2 out of 6, I could count the number of 5s, which is a 1 out of 6. I could count the number of 6s, which is a 1 out of 6, and I could add them together to get 2 out of 6. All right, a couple more, and then we're going to put them all on a table together. If A and B are mutually exclusive, this is the one that I was just kind of referring to. If they are mutually exclusive, then the probability of the union, A union B, if you've taken number theory, you've run into unions. You might have run into them in contemporary math, depending on what your professor in that class chose to work with in that section. It just means the word or. Union means either or true. So this is very much the same example that I just did before. Probably a 5 or 6. And it's the summation of it. So theorem 9.4 is just a different stating of 9.3. Yes?
What does the U upside down?
It means intersection. Do I have it on here somewhere?
Mm-hmm. You had it for mutually exclusive.
Oh, yeah. It just means and.
Okay.
Sorry. I brushed past it because I was describing it instead of looking at the notations. It means and. It means they both happen at the same time. So this is saying that they can't both happen at the same time. And this symbol here, if you haven't seen this before, is an empty set. And again, all this statement is saying is they cannot both be happening. Right? You cannot roll both the 5 and the 6. It's one or the other. Okay, our last one on this screen over here is about something called complements. If A is an event and A bar on top of it is a complement, if you did this notation with our contemporary math book, it uses a notation like that, where it puts like an accent mark on it or an apostrophe next to it if you think of it that way. There's also an equivalent notation in some books that puts a little C up in there like it's a subscript, a superscript, okay? It all means complement. What does complement mean? Well, it means the exact opposite of A, right? So if the event is even, the exact opposite is not even. If the event is rolling a prime number, the exact opposite is not a prime number. If the event is rolling a 5, the exact opposite is not a 5. That's what a complement is. It's the exact thing that it's not, the exact opposite. So what this is saying, if you think about evens and odds, this is a good example for this, is if you take the probability of rolling an even and the probability of rolling something that's not an even, that's all the possibilities there are. It's 100%. If your probability of rolling a 5 plus the probability of rolling something that's not a 5, well, that's all the possibilities there are. And these other two down here are just variations of the first one. They just move the numbers to the side. So in the first one, this one gets subtracted to the side. It creates the first one. In the last one, this P of A gets subtracted to this side and creates the third one. They're not any different kind of formulas. They're the same. All right, so these are all of the different probability properties. And the next table actually just puts them all together. So I'll let you fill them in. And then we'll chat about them. Okay, so if you're writing and you're like, didn't I just write this down? Yes, yes you did. This is just all in a much more compact form. It avoids all the language that you saw happening surrounding the theorems themselves. The first one talks about the fact that the probability of an empty set, something that can't happen, is 0. So think about my die. If I want the probability of rolling a 7 on a single die that goes only up to 6, that's an impossible event. It's 0. The probability of rolling a 7 on a die is 0. The second one is a certain event. What's the probability when I roll the die that some number between 1 and 6 is going to show up? It's going to happen, guaranteed. That probability is 1. It's a certain event. The next line, number 3, says that all the other probabilities are somewhere between 0 and 1. Right? So if an event A is in the sample space, then it's between a 0 and a 1 probability for it to happen. In fact, if it's even outside, it's between 0 and 1. It's either 0 if it's outside, or it's between 0 and 1 if it's inside the sample space. The fourth one says that if you have two events that do not overlap, like 5 and 6, and you want the union, the probability of the union, it's the addition of the two probabilities because they didn't overlap. The only one that's new is this one right here. If you don't have mutually exclusive events and you have the probability of the union, you have the two individual probabilities just like the line above, but you have to subtract whatever they intersect in. For example, if you wanted to count the number of values in that set, like 1 through 6, that are even, there's 3 of them, 2, 4, 6. But if you wanted to look at the numbers that are prime, there's also 3 of them. The prime numbers are 2, 3, and 5. But 2, 3, 5 overlaps with 2, 4, 6 in exactly one number. So if I were to be counting them, I would double count the number 2. And so I have to remove that double counting. So that's why you're seeing the removal of the probability. That would be that number 2 that they overlap in. And then our last one talks about the complements principle at the end that we had on that last screen. The probability of the complement is 1 minus the probability of the event itself. So all that's well and good until we do some problems because you don't see how it plays into each other yet. And it's not near as hard as this table feels like I've just got a whole bunch of new rules to memorize. It's not like that. So let's take a look and you'll see how it works. This is starting off with an example of a deck of cards. And I always like to talk about a deck of cards a little bit because I don't know your familiarity with a deck of cards. Some of you were like, yeah, who doesn't know what a deck of cards is? And others of you were like, yeah, I don't play card games. So write some details down if it's a less familiar topic to you so that you have them to go back to. In a standard 52 card deck, first of all, there are 52 cards. That's important. Half of them are red, so that's 26 are red, and half of them are black. 26 are black. Within the red cards, there are 2 different suits of cards. There are diamonds, and there are hearts. So there are 13 diamonds, and there are 13 hearts. Within the black, there are 2 suits as well. There's clubs, so there are 13 clubs, and there are spades. There are 13 spades. Every deck of cards looks just like this. Each of those suits of cards, so let's focus for the moment and just talk about the diamonds, has 13 cards, right? So there's 13 diamonds, 13 hearts, 13 spades, 13 clubs. And every set of 13 cards matches the other sets. There are number cards that go from 2 to 10. So there's no 1. They start at 2, they go up to 10. There are face cards that are jacks, queens, and kings. And then there's the ace. So every suit, whether it's diamonds, clubs, hearts, or spades, has a 2 through a 10, has a jack, queen, king, and an ace. We are not talking about the jokers in the 52 card deck. That would make it a 54 cards. So they're in there for some games. I know some games use them. That's not what we're looking at. Okay, I think that's enough for us to do the problem. If we encounter something else, I'll mention it. But I think that covers all the bases. Okay, so what we're doing is we're counting what we have. So I mentioned face cards are Jack, Queen, King. Ace are not face cards. Ace are not number cards. Ace is something entirely different, okay? So when this asks us to count face cards, and we want to count the face cards, we've got a Jack, Queen, King, 3 of them, but we have 3 of them in the hearts, 3 of them in spades, 3 of them in clubs, and 3 of them in diamonds. So how many face cards do we have? 12. 3 per suit, 4 suits. I'll write them over here to the side, and I'll put them in order. There are 12. 12 face cards. Out of how many cards total? 52. So if there are 12 face cards, how many cards are not face cards? 40 out of the 52. Now, this particular question does not ask us to find these individual probabilities. What it asks us to do is to decide, once we've found them or at least thought about them, whether or not these two probabilities are equal. Are these equally likely? No. You're far more likely to get not a face card than a face card, right? Almost 4 times as likely, right? It's 12, the 40 compared to the 12. It's a lot more likely you're going to get not a face card. So these are not equal. You could say not equally likely, right? How about clubs? How many clubs were there? 13 out of 52. What's the probability of diamonds?
13 out of 52.
Hearts? And spades? And so what about this one? Are these equally likely?
Yes.
Yeah, they are. These are equal. Or equally likely, if you prefer. How about black cards?
26.
26 out of 52. And red? 26 out of 52. So what about these? They're equal. How about kings? How many kings are there?
3.
More.
Four.
4. There are 4 kings. How many queens are there? 4. How many jacks? 'Let's see what's next. Ace? 4. And if we stopped right there, what would we say? Yes, they're equally likely, but we have a couple more things. Evens. Okay, so what are our even numbers of cards? 2, 4, 6, 8, 10. There's 5 per suit. And how many suits? 4, so there's 20. Yeah. So we have 20 cards that are even. What about odd?
16.
It's 16. Be careful. We want to think that they're equal. They're not, actually. There's not a 1. So we start with 3, 5, 7, and 9. There's only 4 of each suit, so it's only 16. And these then would be not equally likely. Now, if you were specifically asked to find the probabilities that I did on this screen, that's not what we were asked for, you would not leave a single one of them the way that I've written them. Because what can all of them actually do? Simplify or reduce, right? Just like we did back in chapter 6. You would simplify every single one of these. And in fact, as you're doing them, if you don't want to think about counting cards individually, you're welcome to think of them as a sort of comprehensive whole. For example, black and red. You might look at that and say, well, I didn't need to find 26 and 52. I know it's 1/2 and 1/2. The deck splits evenly. I could just say 1/2 and 1/2. You certainly could. And that would be totally correct. Totally fine. No problem. Okay? So another way to think about it. All right, so let's do one that's not a card game. We'll do students. A Civ class is composed of 21 men, 34 women. There are 22 education majors, 13 religion majors, 12 science majors, 5 English majors, and 3 math majors. This assuming business is really important. Assuming no one has a double major. If a single student is chosen at random, what is the probability that the student is ... So we first need to figure out what? How many students are we talking about? So what could we add together to figure that out? Yep, we could add 21 and 34. What else could we add together? You could add all together the majors, right? And they should be the same number if the problem is constructed well. So how many do we actually have represented here? There are 55 students represented here. Okay? So the first question says female. What is the probability if you select a student at random that they are female? 34 out of 55. Okay, can that reduce? It doesn't, right? 55 divides by 5 and 11. 34 divides by 2 and 17 or something like that. Yeah, not good. Doesn't simplify. Okay, cool. How about a science major? 12 out of 55. Will that one reduce? Nope. How about an English or a religion major? Yeah. So how many English majors are there? 5. How many religion majors are there? 13. So 5 and 13 makes 18 out of 55. Does it reduce? No. Okay, are we good so far? The last one actually has 2 different ways to think about it. So take a look. It says neither a math major nor a science major. From 55. So one option is to take 55 and just subtract off the math and subtract off the science. And whether you realize it or not, Kenzie, you're actually doing this last one right here when you do that. You're finding a complement. Okay? So that's the complement approach to doing this. We can definitely do that. So we had 55. How many math majors were there? 3. And how many science were there? 12. So math and science added together would be 15. So we could take 55 minus 15 out of our 55. So that's 40 out of 55. Will that reduce?
Yes.
Finally, I've got one that reduces. All right, so what will they divide by?
8 or 5.
5, yeah. And that will give me what?
8 over 11.
8 over 11. So that's a very good way of doing it. Is there another way of doing it that anyone thought of? Yeah. You could just add all the ones that aren't those majors together. So we had 22 education, we had 13 religion, and we had, was it 5 English? So if you add those together, do you also get 40? Yeah, you do. So a couple different ways to think about Part D. All right, the last examples that I have as we're going through these look more like problem C stuff, at least the next 3 do. A student claims that if a fair coin is tossed and comes up heads 5 times in a row, then according to the law of large numbers, the probability of tails on the next toss is greater than the probability of heads. What is your reply? It's always 50-50. So there's a couple of things wrong with it, and Candace hit on one of them. Each individual toss has absolutely nothing to do with the overall outcome, right? And the same is true when that basketball player goes to the goal, right? Like, we know their likelihood of getting it in, but it may not be 50-50, but they still have a possibility of getting it in and a possibility of not, right? It may be more likely that they will or that they won't. But with a problem with coins, with dice, the probability is fixed every single time, right? It doesn't matter what's happened in the past. So each individual toss is 50-50. In this case, equally likely to occur. Regardless of previous tosses. There's another thing that's sort of glaringly wrong with the argument. Anybody notice it? Look carefully.
A lot of large numbers.
And what's wrong with it, Kaylee? It is. It is a thing. We wrote it down just a minute ago. We wrote down the law of large numbers a minute ago. It's also called Bernoulli's theorem. 5 is not a large number. You're right. Yeah, so also, 5 tosses. Oh, we should spell tosses right, I think. Tosses is not a large number. So we can't even talk about the law of large numbers with something that's not a large number, right? So if we're equally likely to pull out, a head or a tail in any particular toss, if we're just tossing it 5 times, it doesn't even make any sense to talk about that. That's not a large number. All right, let's take a look at another one. The following spinner is spun 100 times. Joe claims that the number 4 will occur most often because it has the greatest area of space on the spinner. What would you tell Joe about his conjecture? Remember, conjecture just means what he's assuming to be true. And what is the probability that 4 would occur on any spin? So we'll start with the first part.
I just came out of geometry. I know vertical angles are.
Okay, so Candace says she just came out of geometry and vertical angles should be equal. What did you want to say, Addie?
Oh, I was just thinking about how, they're all right angles. So they don't, sure it has, more space of the circle, but, the spinner has, I don't know.
The spinner doesn't matter. The spinner doesn't care how much space is outside of its own field.
So what does the spinner care
So,
about, Cora?
If it was, a bigger angle, if the 4 was a bigger angle, then it would matter.
Okay, so the spinner doesn't care about space. The spinner cares about the angle it's spinning through, right? Yeah, you're exactly right. So even though there's more space in the diagram, that's not how the spinner, makes a decision. Not that it makes a decision as an animate object, but you know what I mean? That's not how it works. The spinner is deciding what's going on based on the angle that it's spinning through. So the spinning is unrelated to the area of the region. It's related to the angle it passes through. All of these angles are the same. And Addie mentioned that they're 90 degrees, which is true, or they're right angles anyway. So what is the probability that the spinner lands on a 4? It is a 1 out of 4 because they're all equally likely. So what happens on example 5 when it becomes a dartboard? Yeah. So if it's a dartboard, are we more likely to land in the 4 region? We might be more likely to not hit the dartboard. I don't know. But more likely to hit 4 than to hit 1, 2, or 3, right? Yeah, we are. So in this case, his conjecture is true. Since region 4 has the most area. But without more information, we can't actually find that probability, right? We would need more details in order to be able to calculate how much more likely it is. Okay, we're gonna revisit COVID data. It's got good COVID data. We saw some of this before. Recall, as of August 1st, 2020, the total number of positive cases in the state was 37,731, and the population was 3,956,971. So the first question, going back to this, is what is the probability that someone with COVID, that someone had, I didn't read that right. What is the probability of interaction with someone who had tested positive for COVID? What's the likelihood that you would have actually, talked to them or seen them on the street or something like that? Okay, so we have probabilities here now, whereas we were looking at proportions and ratios before, but it's the same stuff, right? How do we do that? Well, we take the number of positive cases, that's the 37,731, and we divide by the total in our population, 3,956,971. Now, we're not turning this into a percent the way that we were back in Chapter 7. We're just dividing, and we're going to record it to 4 decimals, okay? So grab your calculator, and let's figure out what this is in decimal form.
Is that how it's going to be on the homework too, doing decimal form?
Yes.
Or-
Probabilities are always given in decimal form. They are not given in percentages. There are occasions where they might give you the details at the beginning in a percent form, like chance of rain or something like that. It's a 15% chance of rain, but your answer was what's the probability will still be to put it in a probability form at the end. Yeah. What's the decimal we get with 4 decimals? What do we get?
0095.
0095. And just as a reminder, that means 95 out of 10,000, right? This is the 10,000ths place. We talked about that in Chapter 7. 95 out of 10,000. Or it's approximately 1 out of 1,000. So if you crossed paths with 1,000 people in a given day, one of them, right, given the law of large numbers, would have tested positive at some point up to that time for COVID. Okay. So take a look at one more problem like this. This one's deaths. So deaths was another thing that people were strongly calculating all the way through our pandemic. Also on August 1st, there had been a recorded 549 deaths and 30,282 people who had recovered. So what is the probability of interaction with someone who is currently infected with COVID, right? These people over here were people who had tested positive at some point in the past 8 months or whatever, 7 months, whenever they started keeping track, I started keeping track in April. That's when I started keeping my data. So the past 6 or so months, that's how the numbers had worked out. But they recovered, right? You don't test positive and stay positive forever, right? Some of them test positive, they recover. Others tested positive and eventually passed away. So there's 2 different outcomes, but some of them would have still been positive at that time. So we had our 37,000 number, 731. But of that number, 30,000 recovered. So 30,282 actually were well again, even though they tested positive. And 549 of them were no longer with us, so we couldn't pass them on the street. So they're no longer current to case either. And this is still out of our 3 million number at that point in time, 3,956,971. So what do you get when you subtract those pieces in the numerator?
6,900.
6,900. out of the 3,956,971. And what do you get when you do that to 4 decimal places?
0017.
Okay, so again, numbers, this is 17 in 10,000, or approximately 17 would be almost like 20, right? 2 in 1,000. So you pass people on the street, right? And about 1 out of every, did I write that wrong? Oh, I did. I'm so sorry. This is this one over here is much wrong. It's not 1 out of 1,000. This one was supposed to say 1 out of 100. I apologize. I wrote my number down wrong. I was looking at the wrong line. 1 out of 100. 1 out of 100. So if you passed 100 people, about 1 of them would have had tested positive for COVID. But what the reality is that out of every 1,000 people that you have passed, 2 of them would be current carriers of it with those numbers, right? Assuming they were still going about their everyday business and not staying at home. That's what that's looking at. Does that make sense? So we can look at probabilities for all sorts of things. Games are not the only thing. People were looking at all kinds of probabilities through the pandemic as they were looking at these things. So